Let's get started. Let's get started with the lecture today. Today the lecture is about the wisdom of the crowds. We talk about the wisdom of the crowds, and you will see how, actually that's kind of a very weird topic, how groups can be collectively very intelligent, much more intelligent than individuals just by themselves. So, but before we get started with that, I have a little quiz for you guys. So take out your phone and just answer as best as you can. It's not really working. Not really working for you guys, huh? Now it should work. Okay, now it should work. Oh, seriously? Everybody gets the candy question? Oh, fuck. Yeah. Okay. Yeah, okay. Okay, if you reload, apparently, to get the right question. Okay, so you don't see anything happening here because I deliberately don't want you to see what others are saying, right? So, so let's see where we are. Okay, well, actually, you know, that's one of those things. Who would have known that actually you guys are all collectively on average, you got the ordering of those four animals right. Can you see that? Yeah. So there I have the real weight. These are now average weights of adult males of that animal species, right? So the heaviest is the African elephant. Yeah, that's correct. On average, 4,800 kilograms. Then the second heaviest is the hippopotamus. Yeah, the hippo, 3,700 kilograms. That's also ranked number 2 with those your guesses at the moment as well. 6 people went on that one. Number 3, I don't know, 5 people said it's the rhino. Actually, it is the third heaviest animal here, with 2,175 kilograms, and the lightest one is the giraffe with 800 kilograms. Yeah? If you would have shown me those pictures, I would have had no idea how heavy are those guys. But you see, you actually got the ordering right. And this is no fluke. Actually, that's what's called the wisdom of the crowd. That collectively, you guys are actually much more intelligent than you would think. It comes down to this point that you have some rough idea. You know, some of you might know, oh, it's definitely not the giraffe. You know, the giraffe is a little, I don't know, a little skinny, that guy. While others say, well, it's either the elephant or the rhino. While others say, well, it's either the elephant or the hippo in a way. And then when you apply some randomness over the choices that I left, you get kind of a distribution with that. And that's pretty much what we got right here, right now. So you guys are actually pretty bang on here. I'm actually quite surprised. The first time I'm doing this here, so it's actually exciting to see that it actually works. Yeah. Okay, but we'll have more of that sort later on during this lecture. So what I'll talk today is, first of all, I have to talk a little bit about the madness of the crowd to pave the way for what is the wisdom of the crowds. And then at the end, we'll talk a little bit about when this whole phenomena stops working. When does it fail? And this is where social influence then comes into play. So let's first talk about the madness of the crowd. You know, you have to think about it like nowadays we live in a democratic society where everybody has equal rights and votes, you know, and luckily so. But not too long ago, that was not the case. That was not the case. And there were actually intellectuals, professors like me, who kind of said, the crowd shouldn't have a say in things. The state should be run by the elite, because they are the clever people, right? So why shouldn't they run the state? Why should we open up to all individuals where the madness prevails? And Friedrich Nietzsche, a philosopher, he said that madness is the exception in individuals, but the rule in groups. Ever try to organize a group, come together somewhere? I don't know, I have to have the group pay the bill at the end, I don't know, of a dinner out at a restaurant. Or I don't know, these kind of things. It's like a nightmare, yeah? Like getting groups organized. Or you go somewhere with the group. I don't know, you travel somewhere. This weekend I'm traveling with some friends, and you know, I already see it happening. Every half an hour, somebody else needs to stop, needs to pee, or I don't know, and they're thirsty, they're hungry. You know, try to get a group organized. It's a nightmare. Yeah? It's a nightmare. So there's also like a historian, Thomas Carlyle. He said, "I do not believe in the collective wisdom of individual ignorance." So what? Hang on. Collective wisdom of individual ignorance. He says, how can, when individuals are ignorant, how can more than an individual, like a group of individuals, like a collective, how can that error, that ignorance not be there? Right? How can be a group of people not be as ignorant as at least the individuals in there, or even be more ignorant, even be more stupid than that? Or Gustave Le Bon, you know, he had this quote, "In crowds it is stupidity and not mother wit that is accumulated." And now here we are at this point that I had mentioned earlier, that you know, not too long ago, you know, democracy is a relatively recent invention. Well, it was invented like a while back ago, you know, but in modern times, it's actually not that long, 250 years maybe, you know. So here's a quote from Thomas Jefferson, who says, "A democracy is nothing more than mob rule, where 51% of the people may take away the rights of the other 49. Although you could argue, this is actually, now it's important to kind of think these things through, you know. Actually, of course, I'm a huge supporter of democracy in a way, you know. But at the time, 100 years ago, 150 years ago, people like me standing in front of you would have said otherwise. They would have said, okay, well, let's have our cleverest people run the country. And you might question that in modern times as well. Yeah? You might wonder, how can things happen? Yeah? Isn't that crazy? Yeah? Or I don't know, we're living in interesting times when you are a social scientist. Seriously, it's like a very interesting time. You have Brexit to worry about. You have the states that kind of do whatever they want to do. I don't know, it's like really weird what's going on in our world. You have trade wars that are massively hurting people all over the world. And so the question is, how can that be, or is sort of like, are crowds always as good in making decisions? What I brought now with me is sort of a little experiment that some of you guys might have heard about. We're not going to play it, but I have a little video that I want to show you. Given that the audio system works, if you know me, I have a little Don Quixote fight with this university about microphones and audio systems. But anyway, so this is an experiment that was conducted in social psychology. Solomon Asch, one of the most famous experiments in social psychology. And this experiment shows how individuals actually behave really weirdly in crowds. How they kind of really go away from what they know what the truth is and say something false because they want to be part of that group. Yeah. It's like, has a big impact, has been replicated many, many times. And I have a little video about this now. So let's see how that works.
The Asch experiment is one of psychology's oldest and most popular pieces of research. A volunteer is told that he's taking part in a visual perception test. What he doesn't know is that the other participants are actors, and he's the only person taking part in the real test, which is actually about group conformity.
Please begin. The experiment you will be taking part in today involves the perception of line length. Your task will be simply to look at the line here on the left and indicate which of the 3 lines on the right is equal to it in length. So, for example, if you...
The actors have been told to match the wrong lines. The volunteer will be monitored to see if he gives the correct answer or if he goes along with the opinion of the group and gives the wrong answer. In the first test, the correct answer is 2.
1. 1.
1.
Two.
1. Once again, the correct answer is 2.
3. 3. 3. 3.
3.
The ASH experiment has been repeated many times, and the results have been supported again and again. We will conform to the group. Again, we're very social creatures. We're very much aware of what the people around us think. We want to be liked. We don't want to be seen to rock the boat, so we will go along with the group. Even if we don't believe what people are saying, we'll still go along.
1.
1.
1.
Group dynamics is one of the most powerful forces in human psychology.
1. 1.
Okay, well, it's not just psychology. This is also highly relevant for us, you know, when we are kind of thinking about how individual action actually aggregates and to then what is on the higher level, what is at the macro level. And you see, this is one of those very simple points relating back to the lecture we had like 2 weeks ago, you know, where it's not just, I don't know, individuals know the answer and then they say it, but they influence each other. Yeah, and that kind of has an effect on what we observe at the end of the day. This is sort of like what the group would come up with as a solution. So it's a very fascinating experience, being repeated again and again and again, but still super simple and super cool, in my opinion. So anyway, so let's move on and talk now a little bit about the wisdom of crowds. Yeah? The wisdom of the crowds. And here now I have like another little activity for you guys. So take out your phones. And now I want you guys to look at this little thing. It's a jar, right? It's a jar with candy in it. It's a jar with candy in it. So now please go to this website, and now I'm asking you for your best guess about how many candies are in this jar. And you want to pass it around? I don't know. Feel free to pass it around. Don't open it just yet. We'll get to that point.
Would you mind if there was one less in it?
We'll get to that point. We'll get to that point. Because, to be honest, I have no idea either. That's another one of those life experiments that we're going to do. And we're going to see what it's going to be. Does it work out, or do I need to... Oh, shit, I need to activate this again. Okay, now it should work. Sorry guys for the technology. Once you're out of it for a week, suddenly you don't know anymore how it works. Okay, it's working. So again, you won't see anything happening here, but go to the website and you'll be prompted with the question. Sylvia, I have no idea what is in there. Yeah. Now the clever folks start measuring it, you know, they have to calculate the volume in there, and then, you know. Just give me your best number. Just go straight ahead, you know. Okay, let's see where we look like. Okay, so we're currently standing at around 120, 24, 25, and now people adjust, because they see a number, right? And so actually now what I want you to do is you've seen, we had a rough idea about, what others kind of just guessed. Now I actually want you to discuss it with the person next to you just for 30 seconds, a minute, just talk about it briefly. And then I want you to make a second guess. Yeah, so just talk and discuss it briefly. Okay, it's enough. It's enough. Yeah. We still have a lot to talk about, and the whole point is just to, it's not a complicated thing. You just exchange now the information that you guys had. Yeah? So now you revealed your guess. Now you said, well, I said 150 first, or the other person says, well, I said 50, and then I don't know, maybe now you kind of went somewhere else. So now what I want you to do is kind of give me your second guess on this. Yeah? Okay, so our first guess was 125, around something like that. Now our second guess, the average is lower than that. And now we're at 110, 111. Yeah? So let's keep that in mind. Well, actually, I had asked an expert earlier today, a friend of mine who happens to love candy, yeah. Professor in politics. So his guess was 110. Yeah. So actually, this is pretty close. So let's see. I still have no idea. So where's the candy jar at the moment? Yeah. Okay. So now what I want you guys to do, I want you to take out, let's say, 2 or 3 candies, yeah, and pass the jar on with the number. Right? So that at the end of the day, I want the jar to pass around, you grab your candy, and we actually know how many candies there are. Right? Everything clear? So take out 3 or 4, I don't know, take out as many as you want. Yeah? Give others a chance and pass on the total number, right? So that we know the total number at that particular moment. We need to have that piece of information. Okay, while we do that, what a nice distraction during this lecture. While we do that, let me continue. Yeah? Feel free to open the candy if you want to, I don't really care. Eat it, but keep the number. Have the number and pass it on so that eventually we know the result. Okay, what we're actually experiencing here is a phenomena that has been known in the literature for quite a while. There was an article by a statistician called Francis Galton, who happened to be a cousin of Darwin, Charles Darwin. He was a statistician, he was also other things, and he was one of those English aristocrats who at the time, spent their weekends by going to a livestock fair. Now, a livestock fair, this is where, in Ireland you might know this, yeah, where they kind of exhibit livestock, right? And they exchange ideas about how to breed them, how to farm stuff, and how to run whatever, like what a farmer does. Yeah? And funnily, actually, I happened to be at one of those events. It was like 2 years ago. I was, as a visiting researcher, in Texas for a while. And as one does in Texas, one also goes to these livestock fairs. And then there happens to be a rodeo and things like that, and the animals are being displayed. Coming back to Galton, so what he actually did, he went to one of those livestock fairs, and there was a little game going on there. It was non-scientific at all, right? It was just something that the organizers had started, a little competition where people saw a live display of an ox, yeah, and were asked about the weight of that ox. And Galton thought, that's sort of like a really weird thing to do. You know, he disliked democracy in general to begin with, and he wanted to use this competition to show the problem of allowing large groups of people to vote on a topic. His idea was, well, all those amateurs, they have no idea about the weight of that ox, and actually I can show it. Because people kind of gave their vote, their best guess, and they put it in a box, and afterwards, Galton, as a good social scientist, he worked with that data. So he looked at that data afterwards, and actually it was published 1906 in Nature, one of the first volumes of Nature. So if you look at that, yeah, you find the article by Francis Galton called Vox Populi. So that is about the weight of this ox, and 787 people guessed the weight. You know, some were farmers, some were experts, others had no idea about farming in general and so on. And he collected all the guesses of the competition, right? And then he kind of took all those guesses and he looked at the average guess. The average guess was 1,197 pounds. That's around, I don't know, 550 or 500, around 600 kilograms. So that was the average guess. Well, as it turns out, the true weight of this ox was just 1 pound off, half a kilogram off. Yeah? If I would have asked you about what is the weight of an ox, I don't know. Yeah? Well, so that was like surprising. That was surprising. And actually, as it turns out, you can replicate this experiment as well. And that's exactly what I did in my first year lecture, not last semester because I wasn't teaching it, but the year before I was teaching it. So I asked everybody during the lecture in the sociological analysis and research design lecture the weight of that ox. Well, actually, this is not an ox, this is a cow, and she's called Penelope. I'm not making that up, that is Penelope. Okay, so the average guess among males was 608 kilograms. The average guess among females was 408 kilograms, and the total average guess was 474. So again, without actually talking about this stuff before, and you already see, hang on, it's actually pretty close, right? Wasn't like here, like, I don't know, it's like 600 kilograms, and I didn't tell people that at all, right? Just out of the dark, out of the blue, in the lecture, I showed them the picture of Penelope and asked them about the weight of Penelope. And in this case, you know, the true weight of Penelope was 615 kilograms. So again, it's astonishing how accurate, how close the guess was. You know, then for a moment I thought, okay, maybe I'm in Ireland, maybe people are a little more rural here, you know. But no, you can replicate this in cities, in urban areas, and where not. You know, actually I asked around, there are always a few, I don't know, people come from a farming background, you know, maybe then you have an idea. But if you come, as I do, from a completely different background, I would have had no idea about a cow. Is it like 2,000? Is it like 200? I don't really know. Yeah, I hardly ever lift a cow. With 650 kilograms, you actually don't really want to do that anyway. Yeah. So, but analyzing these results, you know, it turns out that none of the males was better than the average male guess, right? So there was nobody between, remember the male average guess was 608 kilograms, the true weight was 615, there was no single individual that had a number that was less than 7 kilograms away from the true weight of that cow. No male was better than the average male guess. No single individual was better. For females, it was like sort of a different story, like 31% of the females were better. Actually, you could make up a whole story around why, I don't know, there's a gender difference here. Maybe relating to the second part of the lecture where we'll talk about social influence. But over the whole population, only 22 of the students were better than the overall average guess, meaning that 78 did worse than the average guess. So actually, it was a pretty good idea to bet on the average guess here, right? Okay, so this is being replicated. I don't know, there's a famous podcast that did the same experiment, you know, now on a much larger scale. with 17,000 people participating online. You see the true weight of Penelope again in the middle. You see the distribution around that. And again, you see how remarkably accurate the average sort of hits that. If you would actually take the average, you would be pretty much bang on, right? And actually, when they ask experts, experts are not really better in that either. Yeah. And that's actually something the wisdom of the crowd predicts, that experts are not better. Why? Because experts have less diversity, but we come to that point in a second. So the whole thing is called the wisdom of the crowd, and that's now we are at the readings that you guys had to do for this week. James Surowiecki, he wrote this popular science book, but nevertheless, actually I really like these popular science books because oftentimes there's something really in it, and if you are interested in the academic stuff, you look at the references in the back and you can follow up on it. But they try to write it in a way that is understandable for everybody, which is something that I think that all academics should do. But anyway, so he writes, under the right circumstances, groups are remarkably intelligent and are often smarter than the smartest people in them. Groups do not need to be dominated by exceptionally intelligent people in order to be smart. Even if most of the people within a group are not especially well-informed or rational, it can still reach a collectively wise decision. Okay, so that's called the wisdom of the crowd. An example where you actually might know that is the game show Who Wants to Be a Millionaire? Who doesn't know this game show? Everybody knows, yeah. But basically it's a game show where people get asked questions, right? And they have four answers where they can select one of those answers, and they have a couple of jokers. And one of the jokers is to ask the audience. So there's the audience sitting there in the television studio, and the audience has buttons a bit like we have here, and then the candidate can ask the audience. So actually there are three lifelines: the 50-50 joker, phone a friend, and ask the audience. And when you look at that data, I can't remember where I got this from, but anyway, so at some point, somebody actually looked at this data, and the audience was right in 91% of the cases. And sometimes those questions are difficult. Sometimes they are really, 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 really difficult questions. So if you haven't read your Hamlet or whatever, right? Or if you can't remember it, or something else, about Shakespeare, or I don't know, or about the Bible, or I don't know, some weird things where you wonder, I have no clue. Yeah? The audience is still right in 91% of the cases. So what's the mechanism behind that? Well, I already explained it a little bit, that we have diverse knowledge. So when there are four options to select from, and I know that it's definitely not A or B, definitely not A or B. I'm not sure about C or D. I have no idea, but I know A or B is the wrong answer. Right? I kind of randomly roll a dice over those two options. While you know it's A, B, or C, but not D. You know that for sure, but you still have no knowledge about the other ones. So basically what I'm saying is, if I would ask you on the spot which one of that it is, there's no reason why you should get to the right one of the three remaining options. But if I ask a lot of people, and everybody has some partial information, and you randomly choose one of those, you use that partial information in a way by randomly choosing from what you know what it is, or ruling something out, I at the end get a distribution that looks a bit like our distribution of the weight of those animals that I started this lecture with. So that's sort of like the key here. Well, James Surowiecki, he writes about the Challenger disaster. It was like the space shuttle back in the 1980s. Pretty cool thing, but unfortunately it exploded in 1986. There was an accident when the thing started, 73 seconds in it, and there was a big examination. Then afterwards, like a big investigation. What caused this accident? Took months. Took a long time to figure out what was the problem. Eventually, they realized there was a problem with some O-rings that were faulty because it was freezing cold at the time, and so on, right? But it took quite a long investigation to figure that out. However, seconds after, or minutes after the explosion of the Challenger, the company that was responsible for this O-ring, that would only be discovered months later to be the cause for this accident, lost the heaviest at the stock exchange. So somehow the collective wisdom of stockbrokers had very quickly figured out that it was most likely related to that company. So again, it's like one of those phenomena where collective wisdom is not only remarkably accurate, but also incredibly fast in finding something out. And people started using this phenomena. Actually, people started using this phenomena to find this lost submarine that James Cherokee is talking about. It was sort of lost somewhere in the 1960s, somewhere in the Atlantic Ocean. So actually, at the time, it was difficult to find a submarine. They didn't have GPS. How would you know where the submarine is? They actually used the wisdom of the crowd to find it and got very, very close to where it actually was. Another example is like a working paper by this guy from Los Alamos Laboratory, Johnson. So he did a little experiment. He had people, he basically set up a maze, a bit like this, not this one, but a bit like this one, right? And people didn't see the whole thing. They could just choose at every crossing where they were, imagine they were like in that maze, and they had to choose to go right or left. They were just really asked, where do you want to go, right or left? You have to go to the middle and find whatever, the treasure in the middle. And so he gave people this choice. They didn't see the whole maze. They just went left or right and so on and walked then to the middle. And on average, it took people 34 steps to find the middle, to find this treasure in the middle where they had to go. It was like pretty much random guesses. Should I go right or left and so on, right? So then what he did, he kind of took 20 solutions. Basically, you can track back like how people walked through that maze. He took 20 solutions and he put them all on the top of each other, right? And then he started at the entrance of his maze, and then he always went with the majority of those 20 solutions. So if, let's say, 15 people at the first corner said they go to the right, and 5 people said they would go to the left, he went to the right. And so on and so forth, right? So at every crossing, he kind of put all the 20 solutions on the top of each other and kind of went with the majority. That's a little experiment that one can do. As it turns out, just taking 20 of those solutions, even though none of them was particularly good, because people didn't see the whole maze, so just overlaying 20 of those solutions and always following the majority rule, actually he found the fastest way to get to the center of the maze. So again, it's like a dramatic drop from an individual solution where actually individuals don't really know anything here about whether they go to the right or the left. Actually, there is some information embedded in there because eventually they do find it, right? So it's not that there's no information in there, there's partial information in there. And then at the end of the day, overlaying them led to the fastest way of finding this. But anyway, so I want to go on. So the conditions for the wisdom of the crowd. So Cherokee, he says, we need to have a diversity of opinion for this to work. We need to contribute different kinds of knowledge. If we don't do that, it doesn't work. We need to have independence of members, decentralization, and a method of aggregating opinions. Let me briefly talk about diversity. So what is meant by that? Well, you might actually see there are all these campaigns to increase diversity at universities and whatnot, and I'm a huge supporter of that, but actually there's even research around this, which kind of says like having a diverse set of pool actually leads to better problem solving. How does that work? Because bringing new members into the organization, even if they're less experienced and less capable, actually makes the group smarter, simply because what little the new members do know is not redundant with what everyone else knows, right? So if you bring people in who all know the same thing, you don't have any new knowledge. While when you have people that are slightly different, they actually get a different perspective on things, right? And they have a new knowledge that they can contribute. So diverse groups are better problem solvers. Only smart people tend to resemble each other in what they can do. The group as a whole does not benefit from 2 people knowing the same thing. That's the point. There's redundancy in there. When you have 2 people who know exactly the same thing, you don't gain any new knowledge. And to show how this works, I have a little example here from a paper from Hong and Page. And for the master students, that's an exciting paper to look at and to remodel, write a computer simulation for your master thesis. Actually, I did it over the summer because I love these kind of things. And then extended it a little bit, but I briefly tell you the story about how this paper goes. So basically, he sets up an artificial world with, in this case, there are 18 locations that can be occupied in this artificial world, and they have different value attached to it, right? And now the task is for individuals to find the highest value. Now think about this being solutions for a problem, and you can have individuals, they can go and find the best solution. And they go about doing that applying certain heuristics. Yeah? With heuristics, I mean like different strategies that they have, different knowledge that they have, something that they can do. In this case, the red individual the red individual can only walk 9 steps, can only go 9 steps and then another 9 steps. That's sort of the only thing that the red individual can do. While the green individual can go 6 steps and then another 6 steps and then another 6 steps. Now you see these are different strategies. These are different abilities that they bring to the table. And when you start with the red individual, that's where we start. And then after nine steps, the individual reaches the 2 at the bottom. And then after another 9 steps, the individual is at the top. And actually now I made a mistake here because obviously 2 is not the maximum, but 16 is the maximum at the top, right? So that's sort of like the maximum that the red individual can reach. That's all there is. That individual can only take 9 steps. So either 2 or 16, and then we are back at the start, and then, I don't know, another 9 steps, and we're back at 2. So these are all the solutions that can be reached by the red individual. While the green individual can reach different kinds of solutions. The green individual also starts on the top, but then taking 6 steps ends up with 18, and from there taking another 6 steps ends up with 66. So now 66 is the maximum that can be reached. And now you see already a funny thing. If now the red individual would copy the green individual, the red individual would increase the value of the solution from 16 also up to 66. But that's about it. Then they could only reach 66. So now if we take them combined, let's say first the red individual takes 9 steps, and then the green individual takes 6 steps, suddenly we end up with 91. Right? So now collectively, they reach a better solution. They find a higher value, but it only works because they are diverse. It only works because they both contribute something unique to this problem-solving issue. So obviously the paper is a little more complicated than that, but that's sort of like the main story, actually. That kind of, by bringing in diversity, you can reach, we would call this different local maxima. Yeah? You can actually leave a local maxima and get into the global maxima eventually, to get to the highest number. Now we couldn't reach 92 with those 2, but maybe if you have a third individual that can take, I don't know, 3 steps or 4 steps or something like that, maybe then we would end up with the global maximum. But the problem with these kind of things is often that sometimes people get stuck in a local value, in a local maxima, right? And then we want to actually push them out of that in a way. And we can actually do this by either having diversity or another mechanism, and that's equally fascinating in my opinion, is randomness. By once in a while making an error. But actually making errors is evolutionarily advantageous because it helps you to break that kind of rule. It helps you to get out of that and reach another maximum later on. Okay, so that's sort of like a paper for a master's students. Actually, it would be a really nice job for a master thesis to re-implement that. And then we can also talk about social influence. So anyway, now let me talk about influence processes that have been discussed, and they are being discussed over the last few years in the context of the wisdom of the crowd. And here the idea is that the more influence a group's members exert on each other, and the more personal contact they have with each other, the less likely it is that the group's decision will be wise ones. Why? Because we lose that diversity. Right? That's sort of why I asked you again to now talk with each other, because it actually meant we lost the diversity. And according to the theory, that kind of would actually make the guess worse. Okay, so we're running a little bit out of time, so let me now ask, where is the candy jar?
It's here.
It's here.
And we have a gap in the information because we
guys.
came along. Whoever had the last, I believe who's the last number that was up here? No. There are 16 left in it. If everybody took one.
What is the highest number that anybody can remember? Guys, seriously, you're in the second year of the university.
Did everybody take one?
No, I think it's more complicated.
No.
Yeah.
Yeah, so.
So somewhere we lost the number. You just said candy. Yeah? Let's just get the candy. This whole setup. Yeah? Seriously. Nobody remembers the large number.
44. Yeah, 44
Here.
was new, but yeah.
And then it passed over there. Somebody had a higher number.
25.
Yeah. Okay, guys, you are useless. Yeah. You are useless. You lose the number. Well, this is going to be a great story in the common room later on, yeah, where us professors come together and tell about stories about how great our students are. Yeah. And I'm giving a lecture about the wisdom of the crowd. Yeah. I kind of talk about how intelligent you are. And to lose the number. It's like hilarious. Really funny. Yeah, well done. Yeah. Anyway, the last time I did this 2 years ago, students, the average guess was 1 candy off. It was 1 candy off at the time. So actually it totally worked. And actually another time I did this in the Netherlands once. Also students were, I think there at the time, they were 2 candies off. But after they talked with each other, their guess got worse. So it went away, it kind of moved away from the ground truth of what it actually was. It got worse than their first guess where they hadn't talked with each other. And this is sort of like where this fails. This fails when people start talking with each other. This fails when people get influenced by each other. And why? Because then we lose diversity. And there was this experiment that some colleagues of mine conducted, actually in Switzerland, where I just used to be a visiting professor for the last 6 months. And an experiment is a great way of doing research. You have a control condition and you have a treatment. You administer the treatment to one half of the group and the control to the other half, and then you actually see the difference, and you actually really know that the difference is driven by your treatment. Now, it's a very powerful way of getting to the causal origins of things, because otherwise making causal explanations is really, really difficult. Okay, so what did they do in this paper? They had these laboratory experiments, where folks come together, where 144 participants came together. In their case, they were students, and they had to solve estimation tasks. So they were given a job, a little more complicated than counting numbers. Sorry. I just find this hilariously funny that you guys fucked this up. Seriously. Anyway, so they had to do estimation tasks. They were asked questions like, what is the population density of Switzerland? Or what is the border length between Switzerland and Italy? Or how many new immigrants are there to Zurich? That kind of question that, I don't know, you wouldn't necessarily expect people to know. I don't know. Of course they are Swiss, so they have a rough idea, but I don't know the border length between Ireland and Northern Ireland. Yeah. Is it like 100 kilometers? Is it like 250? Is it 300? I have no idea. Yeah. So these kind of questions people were asked, or the number of rapes or assaults or murders in Switzerland. And as it turns out, in that case, also the median and the geometric mean were actually very close to that. But that was not the point of the experiment. The point of the experiment was that people had to do this once. Actually, one set of people did that, and they gave their guesses 5 times. While in the second condition, in the treatment conditions, people actually, in between making their guesses, they were given the information about what everybody else had guessed. Right? So they actually saw, a bit like we did earlier, where you saw the distribution of how many candies did the other people think were in the jar. And we shall never know the answer. Yeah. Great. Participants were also asked about their confidence after each time they made a guess. And the results, I'm rushing through this now, you can read up the paper in more detail. But the result was now when you compare these 2 scenarios, the control setting, which is on the left, the no information case, and you have the treatment case, which is on the right, which is the aggregated information case. So when people actually hear about what others said, and now you have people made 5 guesses over time, and when they hear in between what others guessed, they converge. Yeah? And if I would have waited long enough, I don't know, and asked you again and again, the distribution would have become smaller and smaller, and you would have all agreed, I don't know, or most likely come much closer than where you were to begin with. So the diversity would have been reduced. Yeah? That's what we observe. That's a phenomenon. While it is so, now here they have a measure for diversity in groups, and there they show that in this no information case, the diversity kind of remains, while when people talk to each other, diversity gets reduced. And then we can actually show that such a reduction in diversity necessarily leads to a change in the estimate. Anyway, to cut this short, social influence can undermine the wisdom of the crowd. It doesn't work that well anymore when people talk with each other. There actually has been a very recent paper that is just read recently, 2017. I put it on Blackboard now as well. It's also something for you guys to kind of look at if you want to run a simulation in that context or kind of study this. It's a very fascinating area where people look at, hang on a moment, is it always the case that social influence makes it worse? What if we copy an intelligent individual, somebody who actually had a good guess to begin with? And in their paper, their argument is that people are more likely to change their opinion when they are less confident in their own guess. That people who kind of strongly believe in what they said in the first instance, that they are less likely to change and be influenced by others. And then they look at conditions, and then they actually can show that the network structure matters in that regard, that in decentralized network structures, that then the error gets reduced and we come closer to the true mean, while in centralized networks it actually doesn't. But anyway, that's for another day. So let me finish off with another idea for a master thesis. Re-implement this model by Hong and Page as a computer simulation and extend it by adding social influence effects. And what I did over the summer, actually, I added different kinds of influence effects. And there was this very interesting finding that actually, individually, it would make more sense for individuals to copy the best other strategy, the best individual, right? But collectively, that makes it worse. Collectively, it would be better to copy the worst other individual. So that's sort of like a trade-off where individual interests don't align with collective interests. Anyway, I leave it like that. For Thursday, we have a paper on social influence.